This is going to be 7.1 quiz review for honors physics. So number 1 says that 1 million electrons are removed from a neutral plastic ball. What is the charge? So to do this, we're going to say 1 million electrons are removed, so we're going to say negative 1 million electrons are removed. Now we got to convert that to coulombs to find the charge. So we know that 1 electron is equal to 1.6 times 10 to the negative 19th coulombs. So when we do that math for number 1, we should get the charge on the ball is 1.6 times 10 to the negative 13th coulombs. So that's problem number 1. Problem number 2 says, find the total force on charge 2. So our diagram looks something like this. So we've got charge 1 is negative 2 microcoulombs. Charge 2 is 23 microcoulombs. And charge 3 is 48 microcoulombs. Distance between charge 1 and 2 is 0.69 meters. Distance between charge 2 and 3 is 0.39 meters. And we are looking for the total force on charge 2, so I'll start that one. So, first thing we want to figure out is what direction each force is applied, or each charge is applying the force on charge 2. So, the force 1 applies on 2 is an attractive force, since 2 is positive and 1 is negative. So if 2 is the one that's experienced the force, it's going to experience the force that way, so to the left, and that's force of 1 on 2. Now 3 is a positive and a positive, so that's going to repel. So 3 applies a force left as well on charge 2. So that's charge of 3 on 2. And again, how you want to think about this, we're looking for the charge on charge 2, so we're going to think about that one is moving and all the other charges is stationary. So if 3 and 2 are repelling, 3 is going to stay in one spot and 2 is going to move to the left. And same thing for 1. 1 is attracting charge 2, so 1 stays put and 2 would move to the left as well. So what we're going to do is find those two forces, force 1 on 2 and force 3 on 2, and then add them together since they're in the same direction. So first let's find force 1 on charge 2, and that's going to equal 9 times 10 to the 9th for K times negative 2 times 10 to the negative 6th coulombs. So we have microcoulombs, we have to multiply by 10 to the negative 6 to get to coulombs. And that's going to be times charge 2, which is 23 microcoulombs, so times 10 to the negative 6th coulombs. All that over the distance between them squared, and that's going to be 0.69 meters quantity squared. And we do that math, we should get force of 1 on 2 equal to negative 8 or 0.87 newtons. And remember, we want to drop that negative and just go with the direction we drew up there earlier. So you're going to say 0.87 newtons left. I'm going to shrink this down. Now we need to find the force of 3 on 2. So I'm going to say force 3 on 2. Again, we're going to use K, Q1, Q2 over the distance squared to find the force. So I'm going to say 9 times 10 to the 9th times the charge of 3 is 48 microcoulombs, so 48 times 10 to the negative 6th coulombs times charge 2, which is 23 times 10 to the negative 6th coulombs. All that over the distance between them, which is 0.39 meters quantity squared. When we do that math, we should get 65.3 newtons, and that's going to be, we showed that error earlier, so that's going to be to the left as well. I'll shrink that down. And then our last thing, we just need to add them up. So the total force on 2, they're both pointing left, so we'll just add them together. It's going to be 0.87 newtons plus 65.3 newtons, and that ends up equaling 66.2 newtons left. So now we'll move on to number 3. And number 3 says an electric field of 1,225 newtons per coulomb is produced by a charge of 4.46 times 10 to the negative 11th coulombs. For this field strength, what is the distance to the charge? So what we have here is we have our electric field is 1,225 newtons per coulomb. If our charge is 4.46 times 10 to the negative 11th coulombs, and we're looking for our distance. Let me make that a little bit better question mark. So the equation we're going to use for this one is E equals, so the electric field equals K Q1, this is not Q1, just Q, over the distance squared. So we plug our numbers into that, we get 1,225 newtons per coulomb equals 9 times 10 to the 9th times 4.4, let me move this here, 4.46 times 10 to the negative 11th coulombs, all over the distance squared. Shrink this down a little bit. So we solve for D, and we'll get the distance to the charge. Don't forget to take the square root of it. Distance to the charge is equal to 0.018 meters. Alright, we're moving on to number 4 now. Number 4 says uniform electric field magnitude 4.3 times 10 to the second newtons per coulomb is directed parallel to the positive x-axis. What is the change in electrical energy of a proton that as it moves from x equals 6.5 meters to x equals 1.1 meters? So if we think about what's happening here, for x and y axis here, the electric field is going to be pointed to the right along the x-axis, but our charge is going to be moving to the left because it's going from 6.5 to 1.1, so it's going to be D. So one of those is going to have to end up negative, and the other is going to have to end up as positive for us to get the right answer. So let's write down what we know. So we'll write down our electric field is positive since it's going in the positive x direction, so that's going to be 430 newtons per coulomb. Our charge is the charge of one proton, so that's going to be positive 1.6 times 10 to the negative 19th coulombs. And now our distance, so we're really going to find the change in position, so x, for our distance is going to be equal to our final position, 1.1 meters, minus our initial position, 6.5 meters, and that's going to equal negative 5.4 meters. So now we have what we know. What we're looking for here is distance. Oh, I'm sorry, what we're looking for here is not distance. What we're looking for here is electric potential energy. So the change in electrical energy or electric potential energy. So we're going to say electric potential energy that we gain or lose is equal to negative Q E D. I'll shrink this all down. And we substitute into that equation, we get negative times 1.6 times 10 to the negative 19th coulombs times our electric field, which is 430 newtons per coulomb, times our distance, which is negative 5.4 meters. Those two negatives cancel out, and we end up with our the electric potential energy gained or lost. It's going to be gained in this case since it's a positive answer. It is 3.7 times 10 to the negative 16th joules. So that's answer number 4. We'll move on to number 5 now. Number 5 says a particle moves 7.4 meters along an electric field of strength 67 newtons per coulomb. This electric potential energy increases by 2.6 times 10 to the negative 15th joules. What is the potential difference between these two locations? So in this case, the distance it moves is equal to 7.4 meters. And the electric field is equal to 67 newtons per coulomb. And in this case, it says it moves along the electric field, so we're assuming that's in the same direction. So both of those can be positive since they're in the same direction. And we say that its electric potential energy equals 2.6 times 10 to the negative 15th joules. And that increases, so that's going to be positive, and we're looking for the voltage between the two locations, the potential difference between the two locations. So we actually don't need to use the electric potential energy in this equation because we have the equation, our potential difference equals negative the electric field times the distance. So when you substitute into that equation, we get negative 67 newtons per coulomb times 7.4 meters is what it moved through. And our potential difference between those two locations is going to be negative 496 volts. And let's move on to number 6, our last problem here. 6 says a 11 microfarad capacitor is connected to a 24 volt battery. What is the magnitude of the charge in each plate? So we have our capacitance is equal to 11 microfarads is equal to 11 times 10 to the negative 6th farads. We have the voltage or potential difference from the battery is 24 volts, and we're looking for the charge on each plate of the capacitor. So the equation we're going to use for this is Q, the charge, equals capacitance times voltage. So our capacitance is 11 times 10 to the negative 6th farads. Our voltage is 24 volts. And when we do that math, we get the charge in each plate of the capacitor is 2.64 times 10 to the negative 4th coulombs. So that's our answer. Alright, so that's our 7.1 honors quiz review.